Good morning, good afternoon, and good evening. My name is Alain Cramp, and I am the Director of Public Relations and Communication for the ISRRT, and today I will be the chair of this session on artificial intelligence. We have six speakers today for this session. There will be a Q&A session at the end of the presentation, so please submit your question to the speakers via the Q&A window throughout the session. Our first speaker today is Mr.SimonLysdahlgaard, a research radiographer from University Hospital of Southwest Jutland in Denmark. And the title of his presentation is Detection of Metallic Objects on Digital Radiographs with Convolutional Neural Networks, an MRI contraindication screening tool.
Welcome to one of the projects in artificial intelligence in radiography. This one is called Detection of Metallic Objects on Digital Radiographs with Convolutional Neural Networks as an MRI contraindication screening tool. I do not have any conflict of interest to disclose. So, screening for metallic contraindications before MRI examinations are crucial for patient safety. The contraindications are supplied by the patient's family member, screening of electronic health records, etc. The data we obtain are in the electronic health records, but also in the PEC systems. Current research has shown that we can use AI to screen electronic health records for metallic objects indications. But what about the images? Can we screen patients' images for metallic objects? This study evaluates the accuracy of neural networks in the detection of metallic objects on the radiographs. We used the MUIR dataset, which is the musculoskeletal radiographs dataset from the Stanford University, consisting of a lot of images of the upper extremity. Each anatomical region was stratified into datasets with and without metal. Then we trained neural networks for each anatomical region. And we evaluated the performance with area under the curve, sensitivity, and specificity. This is a flowchart showing how we divided the MUIR dataset into anatomical regions. We divided the elbow, finger, forearm, humerus, shoulder, and wrist. For most of the dataset, we had a lot of images with metal and without metal. But for the forearm and humerus, there were not many images with and without metal, so the dataset size were low here. For each anatomical region, we trained a neural network. For the convolutional neural networks, we used custom sequential models. These are simple neural networks. We used Python as the programming language and then the Keras as the API. Before feeding the images into the neural networks, we resized each image into a matrix of 256 and 256. Then we divided the dataset into a training and validation split of 80% and 20%, meaning we trained the neural network on 80% of the data and then evaluated on 20% of the data. Then we used an epoch of 100, meaning that each dataset went through the neural network 100 times. These are some sample images with and without metal. It should be simple for the neural network to differentiate between images with and without metal because of the high Hounsfield unit of the metal. We also used some data augmentation techniques to increase the dataset size. We rotated each image 0.1 degrees, and then we did something called horizontal flip, just flipping each image. This increased the dataset size significantly. For the results, we made some sample predictions. This is just a wrist with some metal, and the neural network told us there were metal. Another image also telling us there is metal. The last image without metal, though there is this anatomical marker, it tells us there is not metal in the wrist. For the overall results, we had high sensitivities, specificities, and area under the curve for the elbow, finger, shoulder, and wrist. But we have lower specificities for the forearm and also the humerus, meaning that this could be because of the low dataset size. We also used a heat map called the GradCam++. These are the eyes of the neural network. We have some sample images with metal and then one without metal. The heat map shows that the neural network looks at the metal on the two first images, and there's no heat map on the last image. So for the discussion, this reference here has shown that we can use AI to identify common data elements in the electronic health records. But now we have shown that we can achieve high accuracies when looking at the images. But we also need to advance these neural networks for each metal type, or just for MR-safe and unsafe implants. We also need to find out if the neural networks can be used in the DICOM format. The MUIR dataset is not in the DICOM format, meaning that we could lose some information here. We need to do some external validation. We need to use the neural networks on other departments and other hospitals. We also need to investigate the very low specificities for the forearm and the humerus. And also we need to use our neural network on CT images and MRI images. So to conclude, our neural networks does classify radiographs with metallic objects for the 6 different anatomic regions with near perfect accuracy. The rapid and iterative capability of the neural networks allows for expansion and as a substitute MRI screening tool for metallic objects. These are my contact details. If you want to contact me, my email is my working email, and then my Facebook.
Our next speaker is Ms. Joanne Todd, a medical imaging technology student from University of Guyana, and Andrew Garnett. The title of the presentation is Real-Time Quality Inspection of Chest X-rays using Computer Vision System.
Good day. Welcome to the presentation of our research project titled Real-Time Quality Inspection of Chest X-rays using Computer Vision Systems. This research was conducted to fulfill the requirements of a Bachelor's of Science, Computer Science, and Bachelor's of Medical Imaging Technology degrees at the University of Guyana. The research was self-funded and carried out between September 2019 to July 2020. I'll start with giving you a little bit of background. So the ability to assess a chest radiograph is a mandatory skill for medical imaging technologists as well as radiologists. And although a standard medical criteria does exist for evaluating these images, there is no standard evaluation limit. Thus, validating the acceptance of an image is very subjective and inconsistent. This is a prominent issue at health institutions within Guyana. This project aims to create an automated solution to counteract these issues. Our thesis statement read, the use of a convolutional neural network to replace manual quality inspection of digital chest X-rays will decrease the frequency of erroneous results being accepted. Our methodology was conducted in 2 stages, the first of which revolved around the creation of our solution, Sabtu, a convolutional neural network, and the second phase, which was the statistical evaluation of the accuracy of our convolutional neural network. We did this by comparing the results that we obtained from the convolutional neural network evaluation to that of a group of radiologists evaluation. And then we weighed this against an accuracy of 90%, which we obtained from literature. The sample size was calculated using Cochrane's formula, and it was found to be 450 radiographs. And our sample selection was obtained from both online open sources as well as local institutions. Further, the images we obtained were of both posterior anterior and anterior posterior projections of chest X-rays. Our evaluation team consisted of 11 radiologists sourced from the Caribbean and from Canada. They digitally evaluated our testing set of 450 radiographs using the below criteria, which is a condensed version of the standard criteria of evaluating chest X-rays.
Due to facing significant limitations in acquiring a large amount of radiographs from local hospitals in the current pandemic, our testing set comprised of images sourced from online databases such as Kaggle and Chest X-ray 14. Following our study design, we presented these images to be evaluated by the team of radiologists as a base of comparison, and then by our convolutional neural network. Of the 450 images, a total of 420 matched radiologist evaluation, leaving us with a 93% rate of accuracy. We proceeded to calculate the precision and sensitivity scores of 0.965 and 0.89 respectively, and finally an F1 score of 0.93 for our model as a statistical measure of its accuracy. It was also found that of the 23 false negatives present in our results, there is a trend in 7 of them containing rotation, which according to radiologist evaluation was still acceptable. Our project also involved the creation of heat map visualization in effort to analyze the reasoning behind rejections from the model. We used a method known as gradient-based class activation mapping, where areas of the image that contributed to a false evaluation are highlighted red-orange. An example of a match can be found in radiograph 390, where the low density of bones was highlighted in an accepted image, matching with the radiologist's evaluation. We came across several milestones in our research. We found that a convolutional neural network was most suited for the task at hand. Its 93% rate of accuracy outperformed traditional machine learning algorithms, such as k-nearest neighbors and naive Bayes. We also effectively conducted quality inspection for both anterior-posterior and posterior-anterior chest X-rays. We surpassed the calculated baseline of 90% at the beginning of our study, and lastly, we were able to produce a visualization mechanism to assist in future improvements of our model. With our results from the CNN, or convolutional neural network, surpassing the baseline accuracy set of medical imaging technologist evaluation in the hospital, there is hence not sufficient information to accept the null hypothesis that there will be no change in frequency of erroneous evaluations being accepted after the replacement of manual quality inspection with a convolutional neural network. We've also found that in its current state, the highest number of false negatives were attributed to the convolutional neural network rejecting images with a level of rotation considered acceptable by radiologists, showing a mismatch in standard. Lastly, in regard to future work and limitations, we hope to gain access to and label a much larger training set, as well as use a 50-layer ResNet architecture in the development of our model instead of an 18-layer one. We also hope to further eliminate subjectivity and bias in the manual evaluation of the images by having a larger pool of radiologists all evaluate the same set of images and measure the actual error rates over an extended period of time at the local hospital as a baseline. Our vision for this entire project is that with the current average response time being 6 seconds, we can soon improve this so that it can be implemented within the hospital workflow. Thank you for listening. Goodbye.
Hello again. May I remind you that you could use the Q&A chat box to ask any question to the speakers. Our next speaker is Prof.MariaLaw from the Tung Wah College in Hong Kong. And the title of our presentation is Development of Radiomics-based Model for Prediction of Treatment Outcome from Patients with Head and Neck Cancers Undergoing Radiotherapy.
This is MariaLaw. I'm going to present today the development of radiomics-based model for prediction of treatment outcomes for patients with head and neck cancers undergoing radiotherapy. I have nothing to disclose. What is radiomics? It is an area involving extensive mining of medical image features. Such features can be tumors, tissue damage during a course of radiotherapy. Using machine learning, the disease features could be correlated with some meaningful characteristic of a patient or clinical outcome and can be analyzed to form predictive model. For example, tumor tissue damage features can be associated with radiation dose from radiotherapy, personal characteristics, and treatment modalities. Their changes after radiotherapy can be quantified and modeled to predict the treatment outcomes. The predictive model generated using artificial intelligence can be re-evaluated on different patient groups. Thus, this is a dynamic model. So the purpose of this research was to evaluate the performance of radiomics features extracted from the planning target volume, PTV, and the gross target volume, GTV, for the prediction of prognosis of head and neck squamous cell carcinoma. The method was a retrospective study. The diagnostic image, patient characteristics, and radiotherapy treatment planning data were obtained from the internet source. Deep learning and artificial neural networks was used to assess and predict the correlation of GTV and PTV and the treatment outcomes of patients with head and neck cancer. The prediction was used to formulate a predictive model on treatment outcomes. So the method goes like this. First of all, the image features are extracted from the data that we collected on the GTV and PTV. And then correlation of the treatment outcomes was done to formulate our radiomics features like here. And then we evaluate the model to see if it fits for the purpose. And then we use 3D slicer with Pi radiomics extension to extract the GTV and PTV features. Altogether, 107 radiomic features were used to create a predictive model. You can see these features below here. The data were input into the ANN using deep learning algorithm. And the ANN in the current study comprises 4 hidden layers with 107 input and 1 binary output to train the network. The leave one out cross validation was used in this study to evaluate the model, which leaves one data out of the training set as a test data. After the data is tested, this data is put back into the test set. This process is repeated for each and every single datum. The algorithm performance analysis is evaluated using concordance statistics, C-index, which is also the area under the ROC curve. Rocket and SPSS were used to generate the ROC and AUC, or the C-index. So analysis of treatment outcomes prediction is for the prediction of death, we use 90 cases of PTV, and then 45 of them survived after 5 years, and 45 of them died of cancer within 5 years. And they were tested for death prediction model fitting. And then for cancer recurrence, we also use 100 cases of PTV, and then 50 had recurrence within 5 years and 50 without. They are tested for recurrence prediction model fitting. And then here you can see the collection of data and the demographics of our data. And then the results comes like this. For the prediction of death, we use GTV and PTV. And for prediction of cancer recurrence, we also use the same. And here you can see the accuracy of the model, sensitivity and specificity. And the AUC tells us how accurate the prediction could be. Then this is all over 90%. And this is a graphical presentation of the same thing, the GTV and PTV for the prediction of death and for the prediction of recurrence. So for the discussion, this was a pilot study on the use of radiomic features of GTV and PTV to predict treatment outcome. Compared with another study by Bryce et al., the authors used clinical factors like nodal stage, tumor size, stage, resectability, and hemoglobin level to predict a 2-year survival. Compared with Bryce, our model using GTV shows more promising results. As you can see, the accuracy, sensitivity, specificity, and the AUC below, ours had a much higher accuracy. Only the size and shape of tumor were input in this study. Further correlation of image features of the tumor phenotype and genomic features would be possible with the advances in technology. Histological classification using radiomics would further improve the prediction of treatment outcomes. Together, they play a complementary role along with the current TNM system, on which most of treatment decisions are based. The predictive model, when correlate with more of the patient's or the individual's characteristics like age, genome, or biochemical information, would assist in personalized medicine with improved treatment outcomes. So in conclusion, radiomics is a recent development of artificial intelligence that utilizes image information for decision-making. This study assessed the use of ANNs to predict different treatment outcomes and found to yield promising results in the prediction of prognosis and with good predictive abilities. Correlating image data with genomic data and personal and tumor characteristics would be the way to proceed with personalized cancer treatment. So we acknowledge the University Grants Committee for the support of this research. Thank you.
Thank you, Professor Law. Our next speaker is Mr. SimonLysdahlgaard, and the title of his presentation will be Validation of Deep Learning Algorithms for Quality Assessment of Lateral X-ray knee examinations.
Welcome to one of the projects in artificial intelligence in radiography. This one is called Validation of Deep Learning Algorithms for Quality Assessments of Lateral Knee X-ray Examinations. We do not have any conflict of interest to disclose. So, assessing the quality of radiographic images after taking it is one of the major quality decisions of a radiographer. Quality assessment of radiographs differs between radiographers and reporting radiographers/radiologists. The question is here, can we train a deep learning algorithm to be as good as the reporting radiographers and radiologists? For this study, we used reporting radiographers. Our aim was to ask if can deep learning algorithms assist the radiographer in assessment of lateral knee X-rays. Our local audit shows that we take a lot of unnecessary retakes. For the right knee, we take over 30% of unnecessary retakes. For the left knee, we take over 40% of unnecessary retakes. We used a local dataset in this study. This was approved by the National Ethics Committee. We stratified images of the knee into accepted and unaccepted images according to the reporting radiographers. Then we trained algorithms, the neural networks, for both the left knee and the right knee. The performance were evaluated by the area under the curve, the sensitivity, and the specificity. So we took 4,000 images from our local hospital. There were 2,000 of the right knee and 2,000 of the left knee. Then we subdivided the right and the left knee into 1,000 accepted and 1,000 unaccepted. And then we trained a neural network for the right knee and for the left knee. Now we're going into the results, and my partner will present the results.
There are three important parts that should be noted when it comes to the convolutional neural network methodology in the research. That is, the first part is that 5 CNNs have been used, AlexNet, which is an older architecture used as the gold standard, exception, and 3 residual networks with 50, 101, and 152 layers, which are closer to the state of the art. Hyperparameter determination has been performed using a grid search procedure in which various hyperparameters are discretized, and all possible hyperparameter combinations are tested. As shown in figure 1, this approach may not necessarily find the best possible architecture indicated with a star, but it may find one that is, for all practical purposes, really close to it. Finally, the cross-validation is applied, in which the dataset is split into 5 parts, 5 folds. In the process of training and testing is repeated 5 times. In each of these times, one part of the dataset is used for testing and the others for training, with a different part used each time. This allows us to test our models, to see how they perform on different parts of the dataset and how robust they are. In the figures 1 and 2, we can see the heat maps generated by the models. We can see that they generally follow bone structure, although not perfectly exactly. The reason for this is that images haven't been registered and there is some variance between the figures, between the positions of the bone structure. What is important, we can see that heat maps that show that the models haven't used parts of the image that don't contain anything of importance for classification, showing that models are valid. Finally, we can see the scores here with the AUC score on the y-axis and different CNNs on the x-axis. What is important to note is that the poorest performance is shown by the AlexNet for all 3 cases, left, right, and left plus right knees. The variance across the faults is also the highest for the AlexNet. Exception has performed decently well, but the best performing results are achieved by ResNet in general and ResNet 152, which achieves the highest AUC scores and the lowest variances across the faults. This is the most complex network used, and these are expected results. The scores are relatively high and indicate good performance of the models.
And thanks to my partner for showing the results, where we achieved an area under the curve of 0.94. But it's also important to mention that our reporting radiographers had an inter-rater kappa value of 0.8 and 0.88, meaning there was great agreement. There were also an inter-rater kappa of 0.84 with an agreement rate of 92%. So we also need to find out if there is a difference between labeling by reporting radiographers contra radiologists. We also need to include image quality of varying degrees in the dataset. In the dataset, we also need to include knees with metal and advanced diseases. We also need to test the generalizability of the neural networks. We need to make some external validation on other datasets or in other hospitals. To conclude, our model had a performance comparable with that of experienced reporting radiographers, achieving the highest AUC of 0.94. The ResNet 152 CNN architecture may be a supportive tool for reducing rejection rates of lateral knee X-rays examinations. Here are my contact details, my work email, and also my Facebook and LinkedIn.
Thank you for this presentation. Our next speaker is Mr.GuillaumeDAVY from Centre Hospitalier Universitaire de Poitiers in France. The title of his presentation is Limitations of Artificial Intelligence.
Hi everyone, my name is GuillaumeDAVY. I'm a radiographer at the Poitiers University Hospital in France, and I will present you the theme of the limits of artificial intelligence. AI is a collection of techniques that allow machines to perform tasks and solve problems normally reserved for humans and some animals. Therefore, this is an overused term, deviates from the true notion of intelligence. The ImageNet challenge is a competition to classify objects by machines using a database of annotated photographs. There is a clear and continuous improvement. From the year 215, AI makes fewer errors than the average human. In 2019, Avila was interested in AI as a diagnostic aid in lung cancer in association with humans. The use of this tool result is a reduction in false positives and negatives. Last year, McKinney published about its used in breast cancer research. AR has better diagnostic performance than specialist radiologists. According to the authors, its performance could correspond to a second reading by a medical specialist. Subsequently, with the accumulation of different articles, the first meta-analysis appeared. The one dedicated to the search for metastases only by machine show relevant results with a sensitivity and specificity more than 80%. The second meta-analysis focused on comparing the results of the EA versus of human caregivers. Note that this is not just an imaging specialist. The graph from Liu's meta-analysis shows significantly higher sensitivity and specificity of AA than human. Today, we have effective diagnostic performance. Some articles warn about the lack of transparency and clinical evaluation assessment. Does it question the limits of AI in clinical application? We have seen that men and machines are not infallible. In terms of types of errors, several articles find poor concordance between algorithm errors and those of humans. This means that the errors are regularly different and highlights the interest of a complementary of the man-machine duo. The first point concerns the learning phase. AI requires perfectly clean and well-annotated data. However, this creates a gap with the current practice, like in emergencies. AI remains an algorithm using digital data to derive proposals. Now, it's wise to recall Hill's criteria. They make it possible to orient an association relation towards an element of causation. The last four require an human brain. Coherence criteria is considered essential to achieve causation, and it's an extremely difficult task for a computer. The last part deals with the concept of security. As early as 2014, researchers studied the possibility of deliberately deceiving artificial intelligence by adding some type of digital noise. The first image looks as a panda will be identified as a gibbon. Since then, the simplicity and the ease of deceiving the EA progress. Here, we see that AI is 91% certain that this is a picture of a dog. Even today, there is no AI control system. This one works like a black box. No one can explain why it shows such ranks rather than another. Here is a method of hacking AI manually. The stop sign will not be identified because of these few stickers. Imagine one could hypothesize that dishonest people would like to change their diagnosis, in particular to activate financial support by private or public insurance. In conclusion, AI provides interesting performance, especially as a complementary aid. The presence of humans will be essential to monitor the results of AI. This is also validated by the various ethical and security aspects and by the orientations of the various recent laws in different countries. The importance of a skill mastered by humans is paramount. The role of training is reinforced. Thank you very much.
Thank you, thank you, Mr.GuillaumeDAVY. Our last speaker is Mr.SimonLysdahlgaard, and the title of the presentation is The Effect of Gaussian Noise on Pneumonia Detection of Chest Radiographs Using Convolutional Neural Network.
Welcome to one of the projects in artificial intelligence in radiography. This one is called The Effect of Gaussian Noise on Pneumonia Detection on Chest Radiographs Using Convolutional Neural Networks. I do not have any conflict of interest to disclose. So, convolutional neural networks have shown promising results in diagnosing chest X-rays. The chest X-rays with suboptimal radiation dose increases image noise and has the potential to affect neural network performance. However, does an increase in image noise affect neural network performance in a negative way? So the aim of this study is to train and validate neural networks for diagnosing bacterial and viral pneumonia chest radiographs at different image noise levels. We used the public chest X-ray pneumonia dataset consisting of almost 6,000 PA chest radiographs. There were almost 1,600 normal, 1,500 viral pneumonia, and almost 3,000 bacterial pneumonia. We trained neural networks for each pneumonia type and also over 5 Gaussian image noise levels, corresponding to a decrease in exposures. We evaluated the performance with area under the curve, sensitivity, and specificity. This is a flowchart showing how we divided each pneumonia into subdivisions. For the bacterial, we used the normal images and then the bacterial images. And then we added Gaussian noise to the bacterial images over 5 levels. Then we trained the neural network for each Gaussian level. We also did that for the viral part. We used custom sequential models, which are simple neural networks. This was written in Python programming language, and then we used the Keras as the API. Before feeding the datasets into the neural networks, we resized each image into 256 and 256. Then we trained and validated on each dataset. We used a training and validation split of 80% and 20%, meaning that we trained on 80% of the data and evaluated on 20% of the data. Then we used an epoch of 100, meaning that each dataset went through the neural network 100 times. These are some sample images of the Gaussian noise levels. There is a low level of noise on the level 1 and a high level of noise on level 5. There's also some sample images from the datasets where 0 is normal images and 1 is those with pneumonia. Before training the neural networks, we also used some data augmentation techniques. We did something called the horizontal flip, that we flipped each image horizontally, and then we also rotated each image 0.1 degrees, just rotating each image all the way around. Then we increased the dataset size. For the results, we did some sample predictions. We had 2 images which are normal, and the neural network showed that these are normal. Then we had 2 images with pneumonia, and the neural network showed us these has pneumonia. For the results, for the bacteria dataset, we had the 5 noise levels, and we had great sensitivities, specificities, and area under the curves, except for noise level 5, where we had a huge drop in the sensitivity. For the viral pneumonia, we had high sensitivities and specificities all the way down on each noise level. We had some drops in the sensitivity and specificity. We also used a heat map called the GradCam++. These are the eyes of the neural network, which are showing what the neural network looks at when differentiating the images. There's 2 images with pneumonia, and then there's one normal. The heat maps here shows that the neural network looks at the pneumonia part on the images. And for the normal, there's only a heat map over the heart and a little bit on the stomach. So current research has shown that we can train neural networks with very high accuracies for detecting pneumonia on the chest X-rays. There's a high accuracy of 95% and 93.3% for the 2 diseases. But now we have tried to add image noise. But we also need to advance our neural networks for other diagnoses than for the viral and bacterial pneumonia. We can also try to use images in DICOM format, which contains a lot more information. We also need to externally validate our neural networks on other datasets, but also in other hospitals. We need to find out why there is a varying performance for the 2 diseases measured over the Gaussian levels. This is the very huge drop in the bacterial dataset. So to conclude, the performance of our neural network in distinguishing between normal, viral, and bacterial pneumonia was only slightly affected by the introduction of image noise. And if you want to contact me for further research, you can contact me on my working email or on my Facebook or LinkedIn.
Thank you to all our presenters of this session on artificial intelligence. We will now go to the Q&A session. We have one question about how important for a model performance is the training data set. Example, if a chest X-ray training data set has 40% of images with pneumonia, how will it perform in general radiology practice with lower prevalence, example 5%? So not quite sure. The question is asked to maybe, is it Joanne that could answer that question?
I think the question was asked to the last presenter. It seems to be in relation to pneumonia.
Okay. So do we have Mr. SimonLysdahlgaard on? Okay, so it seems like the Mr. Lysdahlgaard is not available right now. I do have a question for Professor Law. Do you plan to use this model for another type of cancer?
Okay, can you hear me now?
Yes.
Yes, this is a test model, a pilot study, which is the data were only obtained from the archive, from the, as you can see from just now. It isn't the prospective study yet, but then it can be used because we're testing whether this model works or not. And so we find it quite accurate. And so we are prepared to proceed with the next stage of the project.
Thank you. Okay, let me go back to the question for Simon. The question was, how important for a model's performance is the training data set? Example, if a chest X-ray training data set has 40% of images with pneumonia, how will it perform in general radiology practice with lower prevalence?
Yeah, I can hear. Yeah. Yeah. thank you for the question. It's a pretty technical answer here, but when we train the neural networks, we need to include this question in our pipeline. So we train our neural networks on 40% of our images, and then we can also train on 30% and 20%, and try to match the general radiology practice, trying to match the 5%. So this is a part of the training of the neural network. Yeah.
Thank you for the answer. Thank you once again. I have a question for Joanne. Do you think that this model could be transferred to another type of X-ray examination?
Thank you for the question. I do actually think it can be, and me and my project partner are currently working on developing it for A&E abdominal X-rays, especially in the detection of bowel obstruction and bowel diseases. Because a convolutional neural network is one which can be modified and one which can be classified to a specific type of data, it's very easy for you to take a base model and then develop and train that base model with a new type of image to make it specific to that type of image, so it's able to classify those images in either a category of acceptance or a category of rejections.
Thank you. And I have a question for Guillaume. With all the with your presentation, Guillaume, do you think that AI will replace radiologists in the future for certain types of examinations?
This is a good question. This is certainly not possible because causality is only for humans, and AI and only numerical link, but not causality.
Thank you, Guillaume. So thank you, Guillaume. I don't have any other question. Let me look at the Q&A. There's no other questions. So once again, I would like to thank all our presenters for this session on artificial intelligence. And most important of all, I would like to thank you, all the radiographers and radiologic technologists, for attending this session on artificial intelligence. Thank you.
Thank you.